surfaces of that object. And that pressure difference sometimes is also referred to as the form drag. So later on today, I'm going to show you by example how each one of those can come into play and how in most problems, both of these components, friction, shear, form drag due to pressure are important considerations. And one has to account for both of them in order to get a good grip of how those forces will counterplay each other. Yes?
Are your shear and pressure forces normal to each other, or what's their relation in terms of orientation?
That's a very good question. How are they related to each other, the shear and the pressure drag, form drag? Let me hold on to that until I come to an example later on, after I develop the concept of the boundary layer. And then I think it's much easier for me to discuss how did each of them come into play. Okay, so let's hold on to that until later, after I develop the concept of boundary layer. Right. So all those are very fair questions. Please don't hesitate to ask me. I think it will make the lecture a little more engaging and also more interesting. So what is this boundary layer? And how does it help us as an engineer to analyze the fluid mechanics aspect? And we're going to spend the next lecture also to develop a set of equations so we can use this concept to do engineering estimate. So here we're talking about viscous effect that's most dominant, so you cannot neglect that. And again, just to repeat myself, we are only dealing with constant density fluid. Compressibility or changing density we have to deal with at a higher level graduate classes. And we will use an academic type geometry called a semi-infinite plate to come up with this concept of the boundary layer. And it's academic because nothing in real world application is semi-infinite. And by that I mean a plate semi-infinite. Let me explain that after I draw the diagram. It's two-dimensional, meaning into the board, it looks always the same. Semi-infinite in the sense that in the x direction, it goes on forever. And that's my x direction. The vertical direction is my y direction. So this kind of semi-infinite plate is what we will later on very rigorously analyze the flow with viscous effect with differential equation of motion, and ask ourselves, how can I deduce the velocity profile within the boundary layer? How can I estimate the drag and the shear, etc.? So upstream of this plate, I have a uniform flow approaching the plate, 10 meters per second, for example. And what we find, based on the following assumption, of zero pressure gradient. That's the simplest case we'll start with, meaning as I go down in x, there's no pressure change. dP dx is zero. And later on, you see why this is an important consideration and help simplify our analysis using the viscous equation of motion. So it's somewhat of a baby step in analyzing some very much more complex problem. So what is a boundary layer on this semi-infinite plate? Invisible to our naked eye, once the uniform flow reaches the plate leading edge, the no-slip condition will immediately apply. So that close to the leading edge, I will have a velocity distribution that close to the plate, very near the plate, I have zero velocity at the wall, so-called the no-slip condition. And then at the finite distance of delta, away from the plate, I have a uniform flow. I didn't draw the diagram very well. So make some detailed correction for it. So what I meant to draw is the profile away from the wall above the dash line, or right at the dash line. Above that, the velocity is undisturbed, still at 10 meters per second. But below that, between that and the thickness, or at the wall of the plate, the velocity changes very drastically over that small distance. And that distance is very small, as I will later on hint on the homework that you have to deal with on the first day. The characteristic of that layer, which we'll call boundary layer, from the leading edge on, is laminar to start with, and then you will go through a transition region, and I use some wiggle here to designate the transition region, upon which, beyond that, the flow of the boundary layer will become turbulent. That reminds you of the flow in the pipe, except that was wall bounded and it's in cylindrical coordinates, where less than 2300 or say 4000, the flow in that pipe is laminar. Beyond that, the flow in the pipe becomes turbulent. Now I have a little different scenario, but similar concept of laminar versus turbulent, in that when the Reynolds number, which in this geometry is defined by a length scale, not diameter anymore, but the distance from the leading edge, x, the rest of the Reynolds number definition remains the same. Density, velocity, viscosity, of which, if this Reynolds number, we call it critical Reynolds number, is about 500,000 based on the definition of the distance from the leading edge. Anything less than 500,000, the boundary layer will behave in a laminar way, meaning layers. Beyond that, if it's greater than 500,000, it will become turbulent, where it's very chaotic, consists of very unsteady small motion that promote mixing. Yes?
How high up does that region continue to extend, or does it kind of flatten out?
That's a very good question that we will later on dive into in more detail. When I say a semi-infinite plate, meaning the x continue to extend indefinitely, I will give you a formula later on without the derivation that will come in about actually 4 or 5 lectures later, where this growth of the boundary layer will continue indefinitely, no bound. If you are down 10 miles, this layer will continue to grow. So that happens, say, for atmospheric study where you have gusts of wind at 50 miles per hour over the surface of the Earth on long distance. This so-called boundary layer will continue to grow without any bound. How much it grows is what we will study momentarily. Yes?
So that Reynolds number is defined, why is it how does the x distance come into play?
The x distance is measured from the leading edge on down, and as I go down the boundary layer, or as I go down the plate, the boundary layer will continue to grow, and allowing this x as the length scale to characterize the Reynolds number, allow me to look at the transition between laminar to turbulent flow. Does that make sense?
Yeah, I thought it would have been y, because it's more like the
Y is
diameter of the.
Y is what I call the thickness of the boundary layer is what I call dependent variables. It's something we as an engineer will actually try to estimate. So at the end of the day, as an engineer, I want to know the thickness, delta, of the boundary layer, which is a function of x.
Okay.
The further downstream I go, the further the boundary layer will grow. Can I have an equation estimate how thick the boundary layer is? And that's what we will do for your homework. Beyond that, to get shear and to get drag coefficient, I'm equally interested in the drag force. So I'm going to come up with formula or formulas. And actually in 2 or 3 weeks, I'm going to derive those equations for you so that I have a tool to estimate how thick the boundary layer is at a distance of, say, a foot from the leading edge of your car hood. And I'm going to also estimate at that location, what is the shear? Is it 10 pounds or is it 100 pounds? And that accumulatively will equate to the drag force that your power in the engine has to produce to keep the car running at constant speed, in addition to the friction in the tires, right? And that's the same phenomena for airplane cutting through air. I want to estimate the shear on the wing and the fuselage so that collectively I can tell you what power of the engine required to maintain the aircraft at constant speed. So we are trying to first develop the concept and later on develop all the formulae to get to those bottom line. Yes?
So if you're looking at your energy equation, because the velocity distribution is changing, your average velocity, for example, at like 0.2 would be less than at 0.1, but your pressure gradient is 0. So does this all do with head loss, or where does that energy go?
I think, first of all, when we analyze the boundary layer, and those are all very good questions, you don't need the energy equation per se yet. Okay? It turns out to get the velocity profile or this quantity, all I need, and you can tell me, are what equation? If I say, give you a quiz next lecture and say what equation you will put down to analyze this problem so that I have a hope of getting the thicknesses and the shear, what equation you will put down for me? I want to get the velocity distribution within this viscous flow. What are the equations you will put down? Continuity, without thinking. You always need continuity, and that's exactly what will happen. What else? What else? How many equations you have at your disposal up to now? The same question I asked you before test 2. This is no different. This is now just adding a compressivity or viscous effect. What other equation you will put down to have a hope? I'm not asking you to do it, I'm just asking for the direction. Momentum, clearly. Momentum equation in x and y, but not Euler's differential equation of motion, because that's for immiscible. You will have the counterpart of Euler, which is called Navier-Stokes, but it's still a momentum equation, x and y. It turns out those are all the adequate equations, and we'll do that. We'll do that in about 2 weeks. We will derive the so-called Navier-Stokes equation, just like we did with Euler, except now we throw in the viscous effect, and if I write the equation down, you fill the whole board, entire board, because it's an x, y direction and continuity. We're going to solve those equations. But energy equation, it turns out, is not needed yet unless they're actually heat transfer. momentum and continuity by itself is all I need to solve for the velocity and the shear. Okay? So unless you're dealing with some energy transfer, like heat transfer, energy equation is not needed yet. Right? All a good question. I think that will give me some idea of how much you understand this concept. Any question on this definition of Reynolds number, which is different from that of a pipe flow? And that now is distant from the leading edge is what is most critical. So an airfoil cutting through air or a submarine sailing underwater exactly experience this phenomena of a boundary layer growth from the nose of the airplane and the nose of the submarine hull. This layer will grow. And the further down you go, you will go from a laminar nature to a transition and finally a turbulent nature. And all those has a first order impact on the shear, on the power required, on the heat transfer, etc., etc. And that's kind of the engineering analysis that people pay you to do in industry. All right? So let me put this concept of boundary layer. So I want to be more specific about the critical Reynolds number so you know how to use it. So let me do it over here. Just like we experienced on the pipe flow, this so-called critical Reynolds number is not a magic black and white number, although for homework purposes, we take 500,000 to be our critical Reynolds number, but there's a whole range, all the way up to 3 million, and it's problem dependent, depending on the what is called the turbulence in the free stream, the surface roughness, etc., etc. But the main concept I want you to remember is that at the distance from the leading edge of length L, a foot, 10 feet, etc., if I calculate the Reynolds number based on definition I've shown, if it's less than 500,000, then that part of the boundary layer from the leading edge to this point L, it will be laminar. Contrary to that, if it's more than 500,000, then the boundary layer will go into turbulence. So for any external flow, I always go through from laminar to turbulent type transition, with no exception. No different than pipe flow. So how does that help us as an engineer analyze this airfoil problem and just pretend the cell is living in the early 1930s in Germany, which I just came back from, and an institute that is known for fluid mechanics study. And if you are familiar with history of fluid mechanics, Prandtl is a professor in a German research institute in a small town called Gerlington. I may not say it very well, but it's the equivalent of Blacksburg. It's just a small college town. So he was responsible for coming up with this concept of boundary layer and allowed the Germans at the dawn of World War II to build very well equipped airplanes, simply because of this concept of boundary layer. In the 1930s, there's no iPhone, there's no computer. Everything's done by pencil and paper. And he, with this concept, revolutionized the analysis of fluid flow over an airfoil by simply recognizing, hey, there's only a small region and it's very thin. You're talking about on the hood of an automobile moving at 60 miles per hour, this boundary layer is a tenth of an inch. A tenth of an inch by the time it hit your windshield. That's your homework. So we call it a very thin layer. Within this layer for car hood that's running down the highway at 60 miles per hour, within this layer of a tenth of an inch, viscosity is dominating. You cannot neglect viscosity. And I'm so glad none of you mentioned the word Bernoulli when I asked you how you would analyze this problem. Because within this thin layer, viscous effect is first order, and there's no way I can neglect that. However, this is where the concept of boundary layer becomes so appealing. Beyond that, away from this invisible thin layer, if I move further away from the wall, how far? Not very far, actually. Quarter of an inch for an airfoil that's typical of an airplane. I can pretend the remaining of the flow. Viscous effect is not important. Just forget it. It's inconsequential. So now all of a sudden, I can look at an airfoil, which I'm looking at different shape to generate more lift and make it also less drag. I can analyze this problem by pretending there's an invisible layer wrapping around the lower and upper surface, which I will call BL, stand for boundary layer. And it's very thin. And you have homework to allow you to estimate how thick those boundary layers are. And like I said, on typical airfoil, you're talking about a quarter of an inch, or at most half an inch. So within this dashed line, which is obviously thicker than the geometric airfoil, I have to deal with viscous effect. It's a very complex analysis. I don't think anyone knows what the slide rule is, but back then in the 30s, that's what people use. You can use a slide rule to